Having spent some time exploring Newton's laws of motion and some of their consequences, we're going to spend this lecture exploring another one of Newton's discoveries and talking a bit about some of the consequences of that. And in this case, that is going to be Newton's law of universal gravitation. Starting from 1666, according to popular legend, Isaac Newton was sitting under an apple tree when the idea struck him that what pulls apples from the tree is the same force that keeps the moon circling the Earth. A force of gravity might account for the motions of the planet in addition to the motions of objects on the Earth. It could account for motions of the moon around the Earth and of the Earth around the sun. While this was first formulated during his plague year, it was not published until 1680, almost 20 years later, because the initial data that Newton got did not match with the theory that he was coming up with. It wasn't until he was encouraged by a friend to take another look at it that he was able to fit the data to theory of universal gravitation. Newton's law of universal gravitation states that the force due to gravity between two objects is going to be the mass of one object times the mass of the other objects over the distance between the centers of masses of those objects squared. It also states that the force from one object to another object is going to be acting on a straight line directly between the two objects' center of masses. So one object is going to be pulled by its center of mass towards the other object, while the other object is also pulled by its center of mass towards the first object. This is going to be important in a later lecture because if you define the origin of your lever arm to be at the center of rotation, which is usually very close to the center of mass of the larger object if you're talking about the moon revolving around the Earth or the Earth revolving around the sun. If you do this, this means that there are not going to be any torques involved because the force is going to act directly along the center of the lever arm with no perpendicular component to cause a torque. This means that angular momentum is going to be conserved in these contexts and is going to explain some of the laws of motion that we are going to see in later chapters. The equation for this force is given by F equals G m1 m2 over the distance squared, where G is just a constant of proportionality that tells you how strong the force is and converts between the units of mass 1 times mass 2 divided by distance squared and forces. This is the more complete version of our weight equation, where weight was given by m times g, where g was a constant on the surface of the Earth, but it was different if you went to different planets or if you went far away from the Earth. And the reason for this is that the force weight is equal to g m1 m2 over d squared, which is equal to ma. So the acceleration is going to be equal to g, the big G, times the mass of whatever is doing the pulling divided by the distance between the two center masses squared. Using this for the surface of the Earth and knowing the distance from the surface of the Earth to the center of mass of the Earth, Newton was able to calculate the product of G times M, but was not able to separate those two variables. The person who eventually found a value for big G was a physicist named Cavendish, who did a very complicated experiment. There was also a physicist named Joly who did a more simple experiment that you can see on the side of this slide. In this experiment, he took two masses, m1 and m2, which were set some distance d apart. He first measured the mass of m1 and then introduced m2, which created a gravitational pull, which caused it to have slightly more weight. And by using a very, very sensitive scale, was able to balance out this extra weight and find how much force was applied by the second mass, whose mass was also known. By knowing both the masses, which we didn't know at the time for the Earth, he was able to separate out this big G value and found that was 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, which means that for two 1 kilogram masses, a distance 1 meter apart, the force that's going to be measured is going to be 6.6 times 10 to the negative 11th Newton, which is really not a lot compared to the electromagnetic and strong and weak nuclear forces, which we will talk about later in the course. Also using this, we can go back to our formula that G 9.8 meters per second squared is equal to big G times the mass of the Earth divided by the radius of the Earth squared. And plugging that in, we yield a mass of 6.3 times 10 to the 24th kilograms for the mass of the Earth. Gravity is also one of the many forces that makes use of the inverse square law. This can be understood by a can of paint which you spray and spreads out as it gets farther and farther away. As you're 2 units of distance away, the can of spray paint has spread out to 4 times as thick of an area, which means that the thickness of each layer is only going to be 1/4 of a layer thick compared to 1 layer thick for the 1 unit of distance away. When you get 3 units of distance away, then it's going to be 9. When you get 3 units of distance away, it's going to be 9 times the amount of area needing to be sprayed, which means that each layer is only 1/9 as thick as the 1 unit of distance. And as you get 4 units of distance away, each area is 16 units of area, which means that each layer is 1/16 as thick as it was when it's 1 unit of distance away. Basically, the inverse square law states that as you go twice as far away, you're going to have 1/2 squared amount of force. Whereas if you go 3 times as far away, you're going to have 1/3 squared equals 1/9 the amount of force. And as you go farther and farther, so as you go 4 units away, it's 1/16. If you go 5 units away, it's 1/25, and so on and so forth as it goes out into the distance. This can be seen in this diagram where if you look at the highest point of the gravitational force field, where a force field is a mathematical model we use to talk about the force that's experienced by a mass at some distance away from another mass. If you look at the highest point of the gravitational force field, you will see that's at the surface of the planet. But as you get farther away, it goes down according to 1/d squared. So if you look at R, the force field at R, it's going to be 4 times as much as the force field at 2R and 9 times as much as the force field at 3R. What is interesting that we haven't really talked about is that from the center of the planet to the surface of the planet, the force field actually goes up in a straight line. And what causes this is that as you are on the surface of the planet, you are being pulled by all of the mass of the planet towards the center of the planet. However, as you get closer to the center of the planet, you delve deeper into the center of the planet, you'll see that some of the forces are going to be pulling you to the right, and some of them are going to be pulling you to the left. So you feel less force than you do at the surface of the planet, and this goes down linearly until you reach the very center of the planet, where there are masses on all sides of you that are pulling equally in any direction. The net force on you from all of the masses acting from the planet is going to be 0 because you are being pulled equally in every direction. Therefore, you have no gravitational field and no gravitational force, as all of the forces cancel out. And the closer you get to the center of the planet, the more the forces cancel out, which is why we see this maximum value as you are exactly on the surface. A very obvious application of gravity is the tides, which is the pull of water towards the moon, which causes water not to be evenly distributed around the Earth. Seen in this very exaggerated diagram, where the moon will pull water because it is more flexible than the hard, rocky surface of the Earth towards it by a few meters at a time. And this is going to depend on the position of the moon as well as the time of day and the distance away from the moon at certain times of the year. The sun also contributes to ocean tides, although it is less than half as effective as the moon in rising tides, even though the sun's pull on Earth is 180 times greater than the moon's pull on Earth. So why aren't tides due to the sun 180 times as large as tides due to the moon? Because of the sun's great distance, the difference in gravitational pulls on the opposite sides of the Earth is very small. So while the sun is going to be pulling on tides the same way, causing the liquid water to rise on the Earth side of the Earth, causing the liquid water to rise on the side of the Earth towards the sun and lower on the side of the Earth away from the sun as both sides experience the gravitational pull on the sun. It is not as big of a deal when it's day versus night because the distance from one side of the Earth to the other compared to the distance from the sun to the Earth is so small that the change in 1 over d squared is basically negligible. It's basically the same distance squared whether you're on the side of the Earth closest to the sun or the side of the Earth farthest from the sun. That said, if both the moon and the sun are in alignment, you're going to get very strong tides, which are going to pull out oblongly, which are going to pull the tides out oblongly as seen on the left diagram. Whereas if the moon and the sun are not aligned with the Earth, then the moon is going to be pulling in one direction and the sun is going to be pulling in the other direction, which kind of just balances out and causes there to not be as strong of tides as you would see otherwise. In addition to these ocean tides, Earth is not a rigid solid, but for the most part is a semi-molten liquid covered by a thin, solid, and pliable crust. As a result, the moon-sun tidal forces produce Earth tides as well as ocean tides. So the magma that's swirling around in the Earth's mantle is also going to be pulled on by the sun or the moon, which can cause the solid surface of Earth to rise and fall as much as a quarter meter twice throughout the day. But in addition to magma and the oceans, in the upper part of the atmosphere, there is an ionosphere, so named because it contains many ions, which are electrically charged atoms that are the result of ultraviolet light and intense cosmic ray bombardment. Tidal effects in the ionosphere produce electric currents that alter the magnetic field that surrounds Earth. These are called magnetic tides. While we have been dealing with Newton's gravity, where we treat gravitational force as a force which is pulling between two objects, Einstein instead looked at gravitational fields as a geometrical warping of four-dimensional space-time. He realized that bodies put dents in space and time somewhat like a massive ball placed in the middle of a large waterbed dents the two-dimensional surface. The more massive the ball, the greater the dent or warp. If we roll a marble across the top of the bed, but well away from the ball, the marble will roll in a straight line path. But if we roll the marble near the ball, it will curve as it rolls across the indented surface of the waterbed. If the curve closes on itself, the marble will orbit the ball in either an oval or a circular pattern. If you put on your Newtonian glasses so that you see the ball and the marble, but not the bed, you might conclude that the marble curves because it's attracted to the ball. If you put on your Einsteinian glasses so that you see the marble and the indented waterbed, but not this distant ball, you would likely conclude that the marble curves because the surface on which it moves is curved, in 2 dimensions for the waterbed and in 4 dimensions for space and time. One consequence of this is that if you have a dense enough mass, then it's going to curve space-time so much that not even light is going to be able to escape from it. We don't know much about what happens when this happens because light is not able to escape, therefore not a lot is able to escape. I think there's something called Hawking radiation which escapes, but what this is called is a black hole, which is called black because light can't get out of it. You also have a theoretical idea that because a black hole warps space-time so much, it can open a path to another part of space-time or another part of another dimension, which, which could allow us to travel through time because time as well as space is warped, which means that if you go in one end of what is called a wormhole, it is possible that the warping of time will make it so that when you come out the other end, instead of just being in a different place, you are in a different time as well. As I said, this is all theoretical. While black holes have been observed, wormholes have not been. Some more consequences of universal gravitation is that because everything attracts everything else, and the Earth is attracting itself together as far as it can, any corners of the Earth have been pulled in. As a result, every part of the surface is equidistant from the center of gravity. This makes it a sphere. Therefore, we see from the law of gravitation that the Sun, the Moon, and the Earth are spherical because they have to be, even though rotational effects actually make them slightly ellipsoidal rather than purely spherical. Another use for gravity is that we've been studying the orbits of planets for a very long time, as said in the first lecture. But by the 1840s, studies of the most recently discovered planet at the time, Uranus, showed that the deviations from its orbit could not be explained by the perturbations, which are changes in the orbit caused by other known planets. Because of this, they were able to predict what mass of a planet and where in the sky it was located based on these perturbations or your changes from the orbit that you would see if it was just Uranus rotating around the sun. Two separate scientists were able to independently predict where a planet would be located and sent these locations to an observatory or to two separate observatories, one for each, and one of them was able to discover the planet later that very night. There's a lot about gravity and the space around us that we don't really understand, and that is very different than it was in Newton's time. So recent evidence suggests that the universe is not only expanding, but accelerating outwards, pushed by an anti-gravity dark energy that makes up some 73% of the universe. Furthermore, the rate at which stars circle within galaxies suggests there is more pulling on them than just masses of visible stars. There is also the pull of some new kind of invisible matter, christened dark matter, which makes up 23% of the universe. Ordinary matter, the stuff of stars, cabbages, and kings, in the word of the book, makes up only about 4%. Everything we've been talking about in this course so far has been about ordinary matter, but that only makes up 4% of the universe. And the other 96%, we're still figuring out. This is still, even though we've been studying this for millennia, there are still things out there in this universe that we just don't understand yet, and that is the job of a physicist and an astronomer going forward into the 21st century.